clarify, some clarification.
I just sort of assumed there were 17 different.
You would assume incorrectly.
All right. The homework is up and running, I believe. I don't think anyone started it, but it is there.
How many problems are there?
19. I looked at it and I don't understand the first, I don't understand.
After class, I'm studying to work on
Your statement.
home. I'm studying.
Are you sick?
No, I just need to work.
Are you sure you ain't sick?
Why do I this?
You think you're actually going to work on homework?
I actually do work on it.
Okay, so here we go. We got 19 problems, fair number of multiple choice, which I know everybody loves. Lots of right-hand rule problems. I know everybody loves those too. Something that you may not be aware of if you've not been in a chemistry class or a particle physics class is that AMU stands for atomic mass unit. So if you're 27 AMU, that means your mass is 27 times the mass of essentially a proton. So if you take the mass of a proton, 27 times that is 27 AMU. That gives, well, you mass of a proton you can look up. Or you can just look up 27 AMU. Just Google 27 AMU and you're good to go. Like if you go up here and you go 27 AMU, it'll tell you what the mass is.
27 fighter squadron.
No. 27 AMU, what is meant by AMU? AMU is an electron. How to convert AMU to kilograms. It should be
Just
here.
go convert 27 AMU.
There you go. So it's 4.4834 times 10 to the minus 26 kilograms.
Nice.
So you can do that. It's not terribly difficult. So you've got a bunch of different particles going through magnetic fields at different angles and in different directions and at different velocities. And in some of these, they want you to they want to know what the direction of the force is going to be on the particle. Some of them want to know what the direction, what the radius of the curvature of the trajectory of the particle will be after it enters the field. Some of them want to know the actual velocity. They want you to calculate the velocity from the field strength and from the velocity itself. You know, they got different things that they're going to ask you. You're going to have to use the right-hand rule a lot. You're going to have to use the equation for the Lorentz force. Here's a different one where you go into a magnetic field, but it's also into an electric field. So there's two plates with an electric field between them, and there's a change in voltage. And they want you to calculate the change in voltage if this is going to work the way they want it to work with this particle coming into it. So they're combining some things from different chapters.
That's a magnetic capacitor.
It's a capacitor with a magnetic field going through it.
Nice.
That is a very commonly used technique for steering particles. So there's lots of different ones going on, lots of different representations of magnetic fields. Here's one where they put a wire through a magnetic field, so that's one that we've talked about already. We'll talk about a little bit more today. They want to know the magnetic field around the wire. So more right-hand rule, but a different right-hand rule. Here's a magnetic field through a coil. Another magnetic field from a wire. Solenoid. Two wires carrying the current. They want to know the forces on them. We're going to learn about that today. Here's different particles going through the same magnetic field. They want you to figure out things about them. Here they want you to figure out the field from the path of the particle. They want to find the magnetic force. Again, Lorentz force. Here's a wire in a magnetic field again. So lots of different versions of things in magnetic fields calculate the force. Nothing that we won't cover or we haven't already covered. Last time we ended up on this different particles in a magnetic field and what they do. Whenever you get a particle moving into a magnetic field, you're going to get some kind of curved path. It's going to follow some kind of curved trajectory. And that's when you use that equation for calculating, this equation right here, for calculating the radius of curvature of that path. So you have a particle that comes into a field, it's going to end up going in some kind of circular path if the field is big enough. If the particle leaves the field before it actually enters into that full circular path, of course it won't complete a full circle. But if that magnetic field is big enough for it to complete that circle, it'll go into that circular path, and you can use this equation: mass of the particle times the velocity of the particle divided by the charge of the particle times the magnetic field strength. And that'll tell you the radius of the curvature of that particle. Which way it turns in the field is going to be right-hand rule, right? You have to figure out the right-hand rule. Make sure that you do the right-hand rule for a positive particle. But if it's a negative particle, you use the right-hand rule and use the opposite direction.
Use the left hand.
You could use the left-hand rule as well. It will also work. You just use the same rule, but use your left hand. That usually confuses people more than anything else. But this equation turns out to be very important for that particle radius, that path radius of a particular particle, a particular field. Okay, now. Oh, we actually got to the Hall effect last time too. We talked about the Hall effect. The Hall effect, let's do a little review here. The Hall effect occurs when you put, usually we talk about the Hall effect in terms of conductors, but it actually can happen in many different materials. It can also happen in semiconductors and other things. But in the Hall effect, what happens is that the charges in the wire will separate from one side of the wire to the other and create an EMF across this material. And so it actually creates a voltage in the material, and that's how you guys were detecting electric fields yesterday, is that device is actually a Hall effect device that measures the potential difference across a material when it's put in a magnetic field. And that potential difference can be calculated using this equation right here. The magnetic field times the length of the material that is in the field that is perpendicular to the field. So that's the perpendicular length of the material in the field perpendicular to it, and the velocity of the particles that are perpendicular to the field. This can also be converted into an equation that uses current, which they'll probably do in the next chapter. But anyway, you put this material into a magnetic field, and then you measure the potential across it, and it's going to be equal to magnetic field times length times the velocity of the particles. And this is actually used to measure blood flow. For example, when you put a magnetic field around a blood vessel, it will create an EMF in the blood vessel, and that EMF can be measured using, a voltmeter. And that's what they used to do, like EKGs and other things, to measure heart. They're meant to measure the blood flow through the heart and blood flow through different vessels. And so here they do an example of this. A Hall effect flow probe is placed on an artery. It's going to apply a 0.1 Tesla magnetic field across the artery, and it's going to we're going to calculate the Hall EMF for a diameter of a vessel that is 4 millimeters. So that diameter of the vessel is your L. That's the length of the material across that magnetic field. So we plug in our numbers. Our 0.1 Tesla are 4 millimeters, which is 4 times 10 to the minus 3 meters. And we know that the blood flow has a velocity of 2 centimeters or 20 centimeters per second, which is 0.2 meters per second. And that's going to give us an 80 microvolts EMF across that, which is easily measurable. Well, I guess not easily measurable in that situation because there are lots of other voltages that are about that size, but can be measured. So that's your Hall effect. Any material that where the charges can separate will the charges will separate in that magnetic field, and then you can, as long as there's some kind of movement of those charges, and then you can measure that EMF and calculate the flow rate. Now, let's use our techniques that we've got in our equations so far to calculate the force on a current-carrying conductor, like a wire in a magnetic field. We're going to use right-hand rule again, similar kind of right-hand rule, although not exactly the same. We're going to put our thumb in the direction of the current. So in this case, we've got a wire that has a current going through the magnetic field, so it's coming out of the page. The magnetic field is going from left to right here. And we're going to use our right-hand rule with our thumb in the direction of the current, so our thumb's coming out of the page. Then we're going to put our hand in the direction of the magnetic field, so our hand is going to go from left to right. And our palm is going to point in the direction of the force on the current-carrying wire, which is going to be up. So this particular wire is going to feel a field upward from this current going through this magnetic field. And the force that we're going to use the Lorentz force, but we're going to, instead of using charge in there, we're going to make a conversion from charge that is moving to current that is moving, and they do this conversion right here because current is equal to the number of charges times the amount of charge per charge times the cross-sectional area times the drift velocity of the charge. You plug all those things in and you get current times the length of the wire in the magnetic field times the sine of the angle between the magnetic field and the current carrying wire. So it's a very similar thing. Instead of Q times V times B sine theta, it's I times L times B times sine theta. It gives you the same calculation essentially. So here's a wire in a magnetic field. The magnetic field is 1.5 Tesla, pretty strong field. The length of the wire that is in the field is 5 centimeters. And the current is 20 amps, and it's going to be 90 degrees to it, so the sine of 90 is going to equal 1, and we'll be good to go. We plug in our numbers. We get 20 times 0.05 times 1.5, and the sine of the angle is 1, and we get a force of 1.5 newtons, which for a wire is a fair amount of current. You know, most wires that are carrying current, or this kind of current, are not that big. And so a 20 amp current can be carried in a wire that's, I don't know, a few millimeters across, not hard to do. And that's that force will be noticeable. It will lift the wire or push the wire or whatever it's going to do. Oh, excuse me. So here they're going to use, this is a nice little demonstration of how magnetic field can be used to push a fluid through a tube. And this is what they call a magnetohydrodynamic drive. They tried to do this in submarines. The problem is that when you do this in salt water, it creates problems in the materials, because materials that have currents going through them react badly, with salt water. It creates a, what's the word for that? I can't remember. Creates some kind of effect in the metal and corrodes the metal rapidly. So they have to invent new metals before they can create a submarine drive that is magnetohydrodynamic drive, whatever they call it. But anyway, there was a great book written about this called The Hunt for Red October, and a great movie as well. Highly recommend both. But anyway, the idea is that you're going to create a magnetic field. Excuse me. Create a strong magnetic field upward through this tube, and then a current across the tube, and that pulls liquid through the tube, and then that of course will cause a thrust through the tube. It's kind of like a jet engine in the water. Magnetic jet engine in the water takes advantage of this type of concept.
No moving parts.
Sorry?
I said no moving parts.
There's no moving parts, so it's very quiet. The only sound that would be made is the movement of the fluid through the tube. So, now this is the most common and most practical use of electromagnetic dynamics here, and that is the motor and the generator. So the idea of this is that you put a loop of wire now in a magnetic field and you drive a current through it. What is going to happen?
It's going to gain an magnetic.
Well,
What kind of current you go up to it?
you're getting ahead of yourself. What's going to happen here, from what we know so far, is that there is a magnetic field going from left to right, and there is a wire on this side. So we essentially can think of this as 4 different wires. One wire with a current going up, one wire with a current going across, one wire with a current going down, and another wire with a current going across. Now, the wires that have a current going across, it turns out we can ignore the current in those wires. Why? Well, because whatever forces might happen there, they're either going to be parallel or anti-parallel to the magnetic field, so that there will be no force on those wires. And when they're not, the forces on those two wires are going to be opposite each other, and they're going to cancel out. So if they're not parallel, like right now it's not parallel. Right now it's slightly off kilter. So if we're going to do the right-hand rule, we'll put our thumb in the direction of the current, which will be this way, you know, kind of into the page at an angle. And then we put our fingers in the direction of the field, which is going to be this way, kind of. And then the force is going to be up, but on the other one it's going to be down. So the force from this wire is going to be upward, and the force on this wire is going to be downward, because they're opposite directions of the current. And so those two forces are going to cancel out no matter what. They're either going to be zero or they're going to cancel out. So we don't care about the forces top and bottom wire. However, the two side wires we do. We put our thumb in the direction of this current on this side, it's up, and we put our fingers in the direction of the field, it's this way. That means the force is going to be sideways. That means this is going to feel a force into the page, and the other one, since its current's going to be opposite, is going to feel a force out of the page. That's going to create a twisting force or a torque on this wire, on this overall loop, and that's going to turn this loop. And when this thing goes when it gets to the other side, it's going to have the opposite force on it from those currents, right? So this thing's going to want to be flipping back and forth in this field. Well, that could be useful, but it'd even be more useful if we could just get it to keep spinning around and around and around, right? Here they show a top view of those forces. A top view of those forces shows the forces doing this on one side, and on the other side doing the opposite thing, right? But the one thing that they don't show is that when this thing is turned completely so that the magnetic field is going straight through the loop, the forces are actually outward. And that's bad, because what that's going to do is it's going to lock it in place. So we've got a little bit of a problem here. We've got great forces that are pointing perpendicular to the loop or slightly off perpendicular to the loop, but they're forces that are going to cause this loop to rotate one way or the other. And that's great. But right here, that's not so good. Because when it's lined up perpendicular, when the loop is perpendicular to the field, it's going to lock in place there. So we've got a little bit of a problem. So we fix that problem by putting what we call a commutator on. Commutators and brushes, we call this. So what we do is, where the connection is that's going to provide current to the loop, to this loop, we break the connection so that there's one connector for each side of the loop. One connector going up the loop and then coming down the other side, it's a different connector. And then we put a gap here, and we put these things called brushes on, so that every time the loop goes around, the brushes switch sides, and the current keeps going the same way through the loop every time. If you consider the loop as its own little entity, it switches direction loop. So every time the loop switches orientation in the magnetic field, the current switches direction. But really what happens is that the forces keep pushing the same way every time, and they push the loop around the same direction every time. So this commutator works well, and you only really need this if you're driving your current with a battery, with a DC source. If you drive your loop with an AC source, then you can just keep going, you're good, because it switches directions every time. It switches directions all the time anyway, right? Because the AC current is going one way, one moment, and then another way the other moment, and then you can drive a motor that way. But anyway, the point is, the purpose of this is that you can keep this motor spinning the same direction all the time because you're switching the direction of the current through the loop every time it goes around 180 degrees. And that's great. So let's take a look at this as a animated thing, as a little cartoon. Let's see.
So does that use the same device for a motor, not a motor, a generator? But
Yeah, a generator, you just turn the loop and it creates the current, but we'll get to that in a minute. What's going on here? Why don't I have any... Oh, I'm not connected to the internet. Why am I not connected to the internet? I don't know. Let's just do this.
Save big money now
Oh,
during
great.
Menards Big Sale. Update your floors with Snapstone porcelain tiles. 12 by 12 tile is $448 a square foot. 6 by 24.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. Let's first start with the simplest DC motor possible. It looks like this. The
So there are your
stator
brushes.
provides a constant
Here are
magnetic
your
field,
commutators.
and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates,
Now, the more coils you put in here, the stronger the force, but also the more mass. So there's a nice balance here between number of coils and amount of mass that you're putting in there to get a motor to work most efficiently.
the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards.
So every time it
This
switches,
ensures that the torque action is also in the same direction throughout the motion. So the
right here, remember right here is where these forces, where this coil wants to lock into position. But what happens right when it gets to that locking position? The current turns off because you're at the gap in the commutator. So what happens here is your current turns off and then the forces go away, so it just keeps rolling. And then once it gets through that gap in the commutator, it will actually create current again, but that current will be going the opposite direction, which was just the right direction to keep this thing rolling.
coil will continue rotating.
Turns off for just a fraction and then
If
goes
you
again.
observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor.
So this kind of DC motor isn't great because when you get to that perpendicular position, it does have to kind of run on its own momentum. You have to turn it off and just let it go. If you keep that current going, it'll lock into place. But if you turn it off and let it go, but that means it's not feeling any force, so it does not accelerate during that time. So it kind of goes vroom, vroom, vroom. While, it has this kind of accelerate, don't accelerate kind of motion. So it's a very kind of choppy motor. And when there's friction involved, it even is more choppy. So how do we fix that? This is what it would look like.
Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system.
Well, that's a heavy.
Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will
So why would they put steel layers in between the loops?
To increase the.
Yeah, to increase the field strength. So that's actually going to make the motor even stronger. It adds more mass, but it makes a much stronger motor.
to enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways. Parallel.
Okay, we'll leave it off. We'll leave that at that point. But that is the basic idea of a motor. And the forces involved here can be calculated using the Lorentz force law. But if you want to calculate the torque, remember that torque is equal to force times the distance between the force where the force is acting and the point where it's rotating, right? So we can actually calculate the force as well. I mean the torque as well. Since there are two forces, we end up calculating a little bit different way. But this is how it is calculated right here. You have the torque is equal to, let's see, what are they using for all these things here? We'll just use this one. So the maximum torque that is involved is, actually not max torque, this is the torque at any particular angle. But the torque that's going to be involved is going to equal the number of, oh, I know what this is, sorry. I was trying to figure out what their letters were meaning in here, but now I remember what they mean. So what they've done here is they've said we have a length of the wire from here to here and a length of the wire from here to here. Each of these forces have a distance that is half the width of this, of this loop. And then the length of the wire, of course, is the length from top to bottom of the wire. And so you end up with the Lorentz force, which is ILB sine theta, but you have to multiply that by the distance to the center of the loop, which is half the width times 2, because you have two forces. So it ends up just being the width. So, but then you have the width times the length in this equation. Well, what's the width times the length of a rectangle? It's the area of a rectangle, and it turns out it doesn't even matter if it's a rectangle. If it's a circle, this works as well. So, and it ends up that the torque on a loop of wire in a magnetic field that has a current going through that loop of wire is equal to the current going through the wire times the area of the wire times the magnetic field going through the wire times the sine of the angle between the loop, which the angle between the loop is the normal at the center of the loop. So the angle between the normal from the loop of wire and the magnetic field. And if you have multiple wires, you multiply by the number of loops. So if you have multiple loops, you just multiply by that number of loops. So this equation right here tells you the torque on a looped wire where there's many loops of wire, n number of loops, where the area of the loops is A, the current going through the loops is I, the magnetic field going through the loops is P, and theta is the angle between the loop and the magnetic field. So this tells you everything, but you have to know all these things to figure it out. But it's not that big a deal. Right here, they tell, I mean, these aren't things that are easy, these aren't things that are difficult to measure. So in this particular example, we have 100 turn square loops. So the 100 is the N, that's 100 loops on this particular current carrying loop. So 100 turns, it's a square loop, and it's 10 centimeters on the side, so we can calculate the area by just doing 10 by 10, or 0.01, sorry, 0.1 times 0.1 if you do it in meters, which you should. The current that's going through it, the I in the equation, is 15 amps. The magnetic field is 2 Tesla, right? And they want to find the maximum torque. Well, the torque is maximum when the angle is 90 degrees, because that's the sine of theta is 1 when we have theta equal to 90. So we plug our stuff into the equation. Theta equals 90 just leaves us with this equation. We need N is 100, I is 15 amps, the area is 0.1 squared. That is that's a mistake right there, and then the B is the magnetic field, which is 2 Tesla. Right here they've made a mistake because they said that our loop of wire is 10 centimeters on a side, and so the area should be 10 centimeters times 10 centimeters, which is 0.1 times 0.1, right? So this should be 0.01, or it should be 0.1 meters quantity squared. They made a mistake here.
10 times 10 is 100, right?
10 times 10 is 100, but you need to do 0.1 because it's 10 centimeters, not 10 meters. So 10 centimeters is 0.1. Yeah, you need to convert it into meters and then square it. They didn't do that. This should be 0.1 times 0.1, which is 0.01. But I think their answer is still correct because the answer should be 30 times 100, which is 3,000. Yeah, their answer is still correct. They just didn't write it correct right here. So this should be 3,000 times 0.01, which is 30. But they have 3,000 times 0.1, which should be 300. Their answer is correct, but their calculation right here is incorrect. Anyway, it's pretty. I mean, calculating these stuff is easy. You're just going to be given some numbers, calculate an area. You might have to figure out an angle. The only thing about the angle is that the angle is a bit tricky. So let me show you why the angle is tricky. Right here, this angle, the angle for your loop. So this is looking at the loop from the top. This is the rotator on the loop. These are each side of the loop. So this is the side wire of the loop coming up on the left and going down on the right. And then there's a wire coming across here. That's the top wire across. So the loop from above, and your magnetic field is going this way. The angle that you measure is you're going to take a normal from the center of your loop outward. So this is the face of your loop. You're going to take a dotted line from the center of your loop, and you're going to measure the angle between that line and the magnetic field. That's theta. Theta is not the angle between this and the magnetic field. It's the angle between this and the magnetic field. Okay? And the difference, essentially you're going to get a 90-degree difference there. And so if you take the sines of those two things, it's going to give you a different answer. So when the wire is lined up with the field, when the magnetic field is going right along the top wire and right parallel to that top wire, that is when your angle is 90 degrees. That's when you get your maximum torque. When the field is going right through the loop, when it's going right through that area, then your angle is 0 degrees, and that's when you get 0 torque. Just so you know. This is also used when you're calculating things like current and voltage in this meter right here, in this Darsenball meter. They have a loop of wire in there that the current goes through that you're measuring, and then they have a magnetic field going through that, and that rotates that loop with a torque. And that's what rotates this, that's what rotates that needle in your Darcy voltmeter. Okay, now we move on to a new law, Ampere's law. So far, we have talked about a couple of different things related to some laws that are important, very important in physics. We've talked about electric field. The electric field, when we're talking about electric field and voltage and things, we are talking about some laws that are called Gauss's law, and also we've actually talked about, well, I guess we haven't really talked about Ampere's law yet. But anyway, Gauss's law is one law that is kind of related to some things we've talked about. Now we're going to talk about Ampere's law, which connects currents to magnetic fields. The fact that currents can produce magnetic fields, similar to Lenz's law. This is Lenz's law here, where you get this magnetic field going around a wire like this. But how it's related to the magnetic field it's created, in other words, calculating the magnetic field it creates, is what we call Ampere's law. And this is Ampere's law here. So this was found by doing experiments over and over again. The magnetic field around a long straight wire is calculated by the current. You use the current, you divide by 2 times pi times the radius of the distance that you want to know the magnetic field at. So at some distance away from this wire, perpendicular to the wire, r, if you want to know the field at that distance, you use this formula. And then you multiply by this constant called mu naught, which is the permeability of free space. It is equal to exactly 4 times pi times 10 to the minus 7 Tesla meters per amp. And this is one of the constants of the universe, one of the most important constants of the universe, in fact. And so this constant, along with the previous one that we learned, which was epsilon naught, makes up some really interesting things that we'll learn about here in a little bit. And some interesting things that Einstein has something to do with. You should not be surprised. But let's calculate the current near a wire. So you have a wire that's going to be put in the magnetic field of the Earth, for example. And we're going to put a current through it. No, sorry. Actually, that's not what we're doing. What we're doing here is we want to create a magnetic field that is twice the strength of the Earth's magnetic field at a distance 5 centimeters from the wire, and we want to know how much current we have to put through it to do that. So we take that equation and we solve it for I, and we get this equation, 2 times pi times r times magnetic field B divided by mu naught. And we want to know how much current, if it's going to be twice the magnetic field of the Earth. The magnetic field of the Earth is 0.5 times 10 to the minus 4 Tesla, so we use 1 times 10 to the minus 4 Tesla as the magnetic field we want to create. Then we plug in the distance that we want to measure this from. It's going to be 5 centimeters, so 5 times 10 to the minus 2 meters. We multiply by 2 pi, we divide by the permeability of free space, 4 pi times 10 to the minus 7, and we get a current of 25 amps. So it takes a lot of current. 25 amps is a lot of current. There's not an outlet in this room that will provide you 25 amps. Okay, so 25 amps of current is what is needed to create a magnetic field, and very close to this wire. I mean, we're looking at 5 centimeters from this wire, and the further you get away from the wire, the weaker that field gets. But at 5 centimeters from the wire, we'll get a magnetic field that is twice the magnetic field of the Earth's magnetic field, which is not a very big magnetic field. So even at 25 amps, you don't get a lot of current from one single wire. Sorry, you don't get a lot of magnetic field from one single wire. That tells us that it's difficult to create a magnetic field, and it truly is. If you want to create a truly strong magnetic field, you have to crank hundreds, even thousands of amps through a wire. And when you start putting hundreds and even thousands of amps through a wire, it creates a lot of heat. We did this once. I actually helped to build, I helped to build a wire. We had to build a special wire that could create a magnetic field that was big. And we actually had to make it out of refrigerator tubing. so that we could pump cold water through it while we were pumping the current through it. Because that was the only way we could keep the wire cool enough and pump that kind of current through it. We were pumping hundreds of amps through this wire and hundreds of gallons of ice cold water at the same time to keep it cold. And even when it was doing that, it was still hot. It was still, the water was coming out steaming hot, and the wire was hot. So it's pretty impressive, the amount of current that you have to pump through wires to get a strong magnetic field. What happens if you put that wire into a loop? If you put that wire into a loop, this is how you calculate the magnetic field at the center of that loop. Mu naught times the current through the loop over 2 times the radius of the loop, and that'll tell you the magnetic field at the center of that loop. And it comes from all these equations we've seen before already. What happens if you have a solenoid, so a whole bunch of loops all looped up into a long cylinder? Well, it's a similar equation still. It's mu naught times the number of loops per unit length. So you have a number of loops per meter in this equation. And then you multiply by the current going through the loop. And that'll tell you the magnetic field inside that solenoid. The interesting thing about a solenoid is that you'll get an almost uniform magnetic field in here. It'll almost be the same field everywhere inside the solenoid. And the longer the solenoid is, the more uniform it will be at the center of that solenoid. Once that magnetic field leaves the solenoid, the magnetic field spreads out and loops around and becomes much less uniform and much weaker. But inside of a solenoid, you can build up a pretty strong magnetic field and a pretty uniform magnetic field. So let's calculate the magnetic field inside of a solenoid. Here, this solenoid is going to be 2 meters long, so that's our L, and it'll have 2,000 loops. So if we take those 2,000 loops and divide it by the L, 2,000 divided by 2 meters, we get the number of loops per meter. So it ends up being 1,000 loops per meter, so 1,000 meters to the negative 1. And that becomes our little n, this number right here, 1,000. Becomes our little n in the equation. We plug it into this equation with the current of 1,600 amps, and we get 2 Tesla. That's not bad. 2 Tesla is a nice big field. But it's still a lot of current. That's 1,600 amps of current. You're going to have cooling on that wire. That wire is not, that's going to have to be either a huge wire, like inches in diameter, or it's going to have cooling built into it. We didn't talk about generators. Why not? Let's look at this. This will tell us about generators. So what a generator is essentially it's a motor that instead of driving a current through it and making it work, we turn it and make a current through it. This is a very simple generator. So here is a loop of coil right here. Here's your magnetic field. And if I want to make this into a generator, what I need to do is I need to create a well, I don't want to do it that way, actually.
You got to spin it.
Well, yeah, I want one that spins, but this one is not a spinning generator. So I want to do that. Actually, let's save it. We'll save it, because in the next chapter we'll explain why it works better. So we'll save generators for next chapter. Okay, so magnetic force between 2 parallel conductors now. So if you have one conductor, one wire, this is how you calculate the magnetic field around that wire. But if you have another wire, you calculate the magnetic force of the first wire's magnetic field on the second wire by taking the current from the second wire and multiplying it by the field of the first wire. So you have the current from the second wire and the length of the second wire multiplied by the magnetic field from the first wire. So this is the equation you get, and if you put them both together, you get the force per unit length. So this is a force per length of wire is going to equal the permeability of free space, that 4 times pi times 10 to the, let's see, 4 times pi times 10 to the 7, whatever. And then you multiply by the current of both wires, and then you divide by the 2 pi times the r, which is the distance between the wires. It's simple. It's just stuff that they're going to give you. You plug it in, you're good to go. So, they don't even do an example. That's lame. So here's an example that's kind of built into this. We have a current, we have 2 wires carrying 2 currents. And what are the currents? They say that they're going to carry 1 amp each, so you do 1 amp times 1 amp, which is 1 amp squared, multiply by the 4 pi times 10 to the 7, divide by 2 pi, and these wires are separated by 1 meter, so you put 1 meter in the bottom there, and you get 2 times 10 to the minus 7 newtons per meter. Not much force. But if the length of the wire is big, it can be a fairly good force. Because this is per unit length, so you always multiply this force times the length of the wire. Where do you have long wires carrying currents?
The power.
Power lines. And you can bet that the power companies know what the value of this force is, and they separate the lines by a sufficient distance so that they don't attract each other and touch. Okay? Because in some cases, these forces are going to push away from each other. In some cases, they're going to pull towards each other. What are the 2 cases? Well, when the currents are going in the same direction, what are the forces going to be? So you have a magnetic field that is going up, that's going around one wire using the right-hand rule, and it's going through the other wire. So the other wire has a current, and then it has a field going upward through it. So you do a current, and then you do your magnetic field going upward. That means this is going to be pulled towards the other wire. So when the 2 currents are going in the same direction, they're going to get pulled towards each other. They're going to attract each other. When they're going in opposite directions, they will repel each other. I think that's correct. Let's check that to make sure it's true. I'm looking for a graphic of this so that we can do the right-hand rule. Just search for it. We just need a nice graphic so we can point it out. Right-hand rule, parallel wires. So the right-hand rule for parallel wires, here we go. Apparently it's in this book, but I don't know where it is. Maybe the next page, I don't know. But here we have 2 wires, current in the same direction. The right-hand rule is going to tell us, this must be the next section. If we put if we use our right-hand rule on the left-hand wire, that shows us that the magnetic field is going around this direction, and that means the magnetic field is going through this other wire. So if we use the right-hand rule on this wire to figure out the force on this wire, that means our thumb goes upward with the orange arrow, our hand goes into the page with the blue arrows, and our palm is pointing towards the left, which is towards the other wire, right? So this wire is attracted towards this wire in this situation. If we do the opposite thing, we find out that the magnetic field is coming out of the page for this wire. So this one has the same direction of current, or same direction of magnetic field, but that means that the magnetic field is going to come out of this other wire. So we use the right-hand rule with the left-hand wire. We put our thumb upward, we put our fingers out of the page, and our hand points towards the other wire. So wires with currents in the same direction attract each other. Wires with currents in the opposite directions repel each other. And on those towers for power lines, there's currents going both directions. They have to make sure that the forces are not going to push wires towards each other ever. Or if they do, that there's not enough slack in the lines and there's enough distance between the lines that they'll ever touch, right? You don't ever want the wires to touch no matter which way the currents are going. So they separate the wires and they allow enough slack. And the slack there has to be two reasons for the amount of slack. The amount of slack is determined by how strong the wire is, because you have to allow enough slack so that the wires won't break. If you put too much tension in the wires will break. So you have to have just enough amount of slack so that they can, so that the wires won't break from the tension in the wire. But also you have to have enough slack, or not so much slack, that the wires, when they attract each other or repel each other, will touch. But then you have to also determine the distance between the wires in that same way. And then you also have to consider wind blowing the wires and other things. There's a lot of things going on just hanging the wires from the poles, from going from power plants to cities. It's not just trivial. You don't just say, oh, we'll just make towers and hang wires. You do that and it's catastrophic. There's a lot of science and engineering involved here in hanging those wires. Very simple thing, but very important. Because those wires are not coated with rubber. Okay? Sometimes they are, but they don't always coat them with rubber because it's expensive, and also it doesn't necessarily help. When you have high voltage wires, you'd have to coat them with so much rubber to protect them, it wouldn't even do them any good. So they coat them with a thin coat of rubber just to protect them from the weather, but it's not going to protect it from voltage jumping through the wire. So that rubber coating is just protecting from the weather, so that they don't oxidize. Otherwise, it doesn't really help any. If they touch wire to wire, there's gonna be current going through. So anyway, that is that. I wonder why that picture's not in this book. If that might be an old picture, or it might be in the other physics book, because there's two physics books. So here's that same equation for mass spectrometry, right? When you shoot particles going into a magnetic field, you can actually calculate what kind of particle it is if you know the magnetic field and if you know the initial velocity of the particle. So you can actually calculate what kind of particle it is. Cathode ray tubes use those same things. Magnetic resonance imaging, or MRI. They used to call this nuclear magnetic resonance because it's actually interacting with the nuclear magnetic resonance. But since the word nuclear has got such a bad connotation, they changed the name of it. They also use magnetic fields in doing echocardiograms and other things all the time. Lots of things. Magnetism used all over the place. It is such a versatile and useful thing. But it is an extremely weak force and an extremely weak field in general. It's difficult to make strong magnetic fields, and so it has its challenges. Now, that is the end of this chapter, and we're done quite a bit early. So, I guess we're just done. Yeah, we'll just be done. Congratulations. We're done.